function where the cost function can be written as a sum. In modern day machine learning parlance, these are also called finite sum problems in case you run into that term, and they're just called finite because n is finite here. In pure optimization theory parlance, n can actually go to infinity, and then they are called stochastic optimization problems. Just for terminology, if while searching the internet you run into some such terminology, so you kind of know what it means. So here is our setup in machine learning. We have a bunch of training data. Okay, on this slide, I'm calling x1 through xn. These are the training data, the raw features. Later, actually, I'll stop writing x for them. I'll write them with the letter A, but hopefully that's okay. So x1 through xn, these could be just raw images, for instance, in ImageNet or some other image data set. There could be text documents. There could be anything. y1 through yn, in classical machine learning, think of them as plus minus 1 labels, cat, not cat, or in a regression setup as some real number. So that's our training data. We have d-dimensional raw vectors, n of those, and we have corresponding labels, which can be either plus minus 1 in a classification setting or a real number in a regression setting. It's kind of immaterial for my lecture right now. So that's the input. And whenever anybody says large-scale machine learning, what do we really mean? What we mean is that both n and d can be large. So what does that mean in words? That n is the number of training data points. So n could be these days